So we have got two sets, that is, one is about isomerism, another is some problems. So we come to the next topic, namely isomerism. So many organic compounds, they can exist in the form of isomers. So isomerism, you might have studied about isomerism. That means two or more compounds, they are different compounds, they have the same molecular formula, but they are actually different from each other in their properties. Their physical properties are different, their chemical properties are different, reactivity, melting point, boiling point, density, solubility, everything is different. So such compounds having the same molecular formula, but actually they are different from each other, they are called isomers, and the phenomenon is called isomerism. So such a isomerism, it is very common in organic compounds. So how they are classified, what are the examples, so what are the different types of such isomerism, how do you explain, and we might have studied something about structural isomerism. So isomerism is broadly classified into mainly two types. One is structural isomerism and another one is stereoisomerism. So here they have given, so the compounds which possess the same molecular formula but differ from each other in their physical and chemical properties are called isomers, and the phenomenon is called isomerism. So the isomerism is due to the difference in the arrangement of atoms within their molecules. So broadly we have two types of isomerism: structural isomerism and then stereoisomerism. So structural isomerism, so it is due to the difference in the structural formula. So what are the different types of structural isomers? Similarly, stereoisomerism, it is also called as a space isomerism. What are the different types of stereoisomerism? How do you explain? And what are the different examples? So coming to the first type, the structural isomerism, say when the compounds containing same elements and made up of the same number of atoms of each element have different modes of combination of atoms, the phenomenon is called structural isomerism. The structural formula is different for such compounds. Same molecular formula, structural formula is different. Then, in other words, structural formulas have same molecular formula but different structural formula. Thus, the structural isomerism arises from the difference in the structure of the molecules. So, further, such structural isomerism is of the following different types. What are they? They have given some types: chain or nuclear isomerism. Second one, position isomerism. Third one, functional isomerism. Fourth one, metamerism. Fifth one, ring chain isomerism. And sixth one, tautomerism. We have ring chain isomerism and tautomerism. T-A-U. So, what are these different types? What are the examples? Tautomerism. T-A-U-T-O. Tautomerism. So, we will see what are these different types. Now, this structural isomerism is also called as constitutional isomerism, another name. Structural isomerism may also be called as constitutional isomerism, which is not given here. Then, so one by one, what are these different types? Chain isomerism is also called as nuclear isomerism. Now, what is this type? Have you heard of? Have you studied about this type of isomerism? Structural isomerism, position isomerism, sir? No? Huh? You have studied already. So, we will just see again, but later, under geometrical isomerism, optical isomerism, we have more things to remember. But here, these are simple. So, chain isomerism, chain structure is different. Maybe one straight chain and another branched chain. For example, we have the following 1, 2, 3, 4, 5 examples. First example, see, it is butane. What is the molecular formula of butane? C4H10. We have N-butane, isobutane. Both of them, they are different compounds. One may be more stable, another may be less stable. One may have higher boiling point, another may have lower boiling point. One may have higher melting point, another may have lower melting point. One may be more reactive, another may be less reactive. So, their properties are entirely different. They contain, say, primary, secondary, or it can be primary and tertiary hydrogen atoms. tertiary hydrogen atoms are more reactive than secondary, more reactive than primary, etc. You might have just noted earlier while studying the different types of carbon and hydrogen atoms. Anyway, now butane can exist in two forms, namely N-butane and isobutane, which are chain isomers or nuclear isomers. Then in the case of pentane, see N-pentane, isopentane, neopentane. N-pentane is simply the linear chain. All the 5 carbon atoms are in the form of a straight chain. Isopentane, iso means CH3, CH3 towards one end. On the second carbon atom, there is a methyl group, which is iso. So isopentane. Neo means we have 2 methyl groups attached to the second carbon atom from one end. So therefore, it is neopentane. Similarly, neohexane, neoheptane. So if the group towards the end, CH3, C, attached to 2 more methyl groups, then it is neo. That is the common name. We have seen earlier common names or trivial names. So in pentane, we have such 3 isomers, which are chain isomers or nuclear isomers. The nuclear chain is different. Then butyl alcohol. See, it can be normal butyl alcohol or isobutyl alcohol or tertiary butyl alcohol. All of them contain OH group. So the chain structure is different. In normal butyl alcohol, the 4 carbon atoms are in the form of a straight chain. Then isobutyl alcohol, I have told you, iso stands for CH3, CH3, one end of the chain. Whereas tertiary, it contains neo type of grouping. So it is tertiary butyl alcohol. So the chain structure is different. They are chain isomers. We have another example. We have ethyl benzene and dimethyl benzene. Ethyl benzene contains ethyl group attached to the benzene ring, and dimethyl benzene 2 methyl groups at different positions in the benzene ring. They are also chain isomers. Remember. Then position isomerism. Now position is different. What is position? Earlier chain is different. Here position is different. Position of what? Position of the functional group. What is a functional group? One which decides the functions of the compound. Maybe a double bond, maybe a triple bond, maybe OH group, maybe COOH, maybe any functional group, maybe NH2, NO2 or chlorine or anything. It is different positions. So we have the following examples. Directly see the examples. We have N-propyl alcohol. It is also called as propan-1-ol. Then we have isopropyl alcohol, not isobutyl. Isopropyl alcohol. Because only 3 carbon atoms. It is propan-2-ol. So what is the difference here? Is it the chain, carbon chain? Answer is no. Then is it the functional group? Functional group is same. But the position of the functional group is different. So it is attached to the first carbon atom or second carbon atom, middle carbon atom. So they are position isomers. Then if you take the second example, we have 1 butane, 2 butane. What is the difference? The difference is in the position of the functional group. What is the functional group? Double bond is a functional group. Triple bond is a functional group. I have told you already. Therefore, it is at the end of the chain or the middle of the chain. So they are also position isomers. 1 butane and 2 butane. Then position isomers of methyl pentane. See, pentane is 5 carbon chain. Then methyl group is attached to the second carbon atom or third carbon atom. The position of the substituent methyl is different. So they are also position isomers. They are not chain isomers, remember. Because the main chain is same. 5 carbon, that remains same. Only the substituent methyl. So don't consider it as chain isomers. They are position isomers. You should not confuse. Then coming to the fourth example. Disubstituted benzene shows position isomerism. Position of what? The substituent. In 1,2 positions, 1,3 positions, 1,4 positions. So when 2 methyl groups are attached to the benzene ring, they are called xylenes. XYLENE. We have orthoxylene, methoxylene, paraxylene. What is the ortho position? 1,2 positions are ortho positions. 1,3 positions are meta positions. 1,4 positions are para positions. So the positions are different. Position of the substituent is different. Here it is not the functional group. It is the substituent, methyl group. So they are also, say, position isomers. Then functional isomerism. Here, what is the difference? Functional is different. Functional group is different. So we have just see the following examples. First example, ethyl alcohol, CH3, CH2OH. Then dimethyl ether, CH3, OCH3. both of them are represented by the same molecular formula C2H6O. You know, C2H6O. But first one is alcohol, boiling point 78 degrees Celsius. Another is dimethyl ether, boiling point 36 degrees Celsius. See the difference, half of it. One is forming strong hydrogen bonds, another is not so. One may have higher boiling point, lower boiling point, more soluble in water, less soluble in water, etc. Their properties are entirely different. Reactivity is different. One undergoes hydrolysis, another will not undergo hydrolysis, and so on. So one is alcohol, another is ether. So they are functional isomers. Same molecular formula, but functional group is different. What are the functional groups? First one is alcoholic OH, second one is ether O. Then another example. We have propionaldehyde. It is also called as propanal IUPAC system. Then it is isomeric with acetone or propanone. One is aldehyde, another is ketone. Both have the same molecular formula, that is C3H6O. C3H6O. Then carboxylic acids are isomeric with esters. So we have propanoic acid, IUPAC name. Then we have methyl ethanoate or methyl acetate. Both have the same formula, that is C3H6O2. C3H6O2. But one is carboxylic acid and there is ester. So one may have higher boiling point, another may have lower boiling point. So their boiling point and other properties are entirely different. The functional group itself is different. We have another example, fourth one. Aromatic alcohols are isomeric with phenols. Which are aromatic alcohol? For example, benzyl alcohol, benzene ring, CH2OH. And another one, it is cresol. What do you mean by cresol? When CH3 and OH are present in the benzene ring, they are called cresols. We have orthocresol, metacresol, paracresol, depending on the positions 1, 2, 1, 3, 1, 4. So anyone, say it is orthocresol, it is isomeric with benzyl alcohol. Which isomerism? Functional isomerism. Why it is different functional group, even though they contain OH group? Because first one is alcohol, second one is not alcohol, it is phenol. So phenols are acidic compounds. Cresol is an acidic compound. It is a phenolic compound. Why it is phenol? OH group is directly attached to the benzene ring. Then it is acidic compound. Do you know this one? Phenols are acidic compounds. What is a phenol? Where OH is attached directly to benzene ring. It is acidic compound. Whereas OH is attached to the side chain CH3OH, C2H5OH. They are alcohols. Are they acidic compounds? Answer is no. They are neutral compounds. So OH may be in the form of HOH or NaOH or ROH or C6H5OH. So HOH, neutral. ROH, alcohol, neutral. NaOH, it is alkali, base. Then we have C6H5OH, phenol, acidic compound. So the OH may be in different positions, in different forms. So here, the right side is cresol, means phenol, phenolic compound. Orthocresol, metacresol, paracresol, depending on the position. Left side is alcohol, because OH is not attached to the benzene ring. It is attached to the side chain. So first one is neutral, second one is acidic compound. So what is the difference? Difference is the functional group. Even though both of them say contain OH group, they are not the same OH groups. Alcoholic as well as phenolic. So they are different functional groups. So we have functional isomerism. Huh? Difference? Density. For phenol, right side. When the OH group is directly attached to the benzene ring, orthocresol, OH and CH3, OH is attached directly, it is acidic compound. Whereas first one is neutral compound, not acidic. So they are different functional groups, so they are functional isomers. Then we have, say, ring chain isomerism. The fifth example, we can take it as ring chain isomerism. On the next page, probably. So why it is ring chain isomerism? See, butane. Which butane? It is 1-butane. What is the formula? C4H8. So the ring is cyclobutane. Is it not cyclic compound? Or methyl cyclopropane. It is also cyclic compound. So all these three have the same formula. What is the formula? C4H8. One is chain structure, another is ring structure. So ring chain isomerism is this type. Ring chain isomerism. These are only some examples. You may have many examples. Then metamers. Which are metamers? Metamerism is due to the different hydrocarbon group being attached to the bivalent or polyvalent functional group. The isomers are called metamers. So take the examples. Now first one, the two compounds given, they are ethers. This is the first ether, ethyl ether or diethyl ether. So on both sides of O, we have ethyl group and ethyl group. In another one, it is also ether, but it is not dimethyl ether. What is it called? Methyl propyl ether. What is the difference? One side methyl, another side propyl. But totally, number of carbon atoms, hydrogen atoms, oxygen atoms are same. Molecular formula is same. Structural formula is different. It is a type of structural isomerism called metamerism. Metamers are those where the alkyl groups adjacent to the bivalent or polyvalent functional group is different. So we have seen ether. Then it may be in ketones also. The second example is a ketone. So what is that ketone? We have diethyl ketone or 3-pentanone. So on either side of CO group, we have ethyl and ethyl. But in the other example, one side methyl, another side propyl. The molecular formula is same, 2-pentanone or pentane 2-one. So the alkyl groups are different. So they are also metamers. Need not be in ether, need not be only in ketone. It can be in amines or it can be in esters and so on. So if you take the third example, we have C2H5, C2H5, C2H5. That is C2H5 thrice N, triethylamine. If you take the other example, one is methyl, another is ethyl, third one is propyl. In the other example, we have butyl, methyl, methyl. So the alkyl group attached to the nitrogen atom, they are different. So they are also metamers. They are also metamers. So therefore, about a bivalent or polyvalent functional group, ether, oxygen atom, is it not bivalent? On either side. Ketonic CO, bivalent. Then we have nitrogen, trivalent. Is it not? The ester group CO, it is also bivalent. So like that. CO is ester group. There also it can be methyl and ethyl, or this side ethyl and that side ethyl. Different groups. They are also metamers. Anyway, we have metamers are these types of compounds. Then one more we have already noted, tautomerism. So take for example CH3 CHO. CH3CHO is called ethanol, acetaldehyde. So it can also exist in this form, CH2CHOH. Both have the same formula, that is C2 then H4O, C2H4O. And this form is called keto form. This form is called enol form. Keto means carbonyl, C double bond O group. Enol means, en means double bond. Ol means alcohol. Double bond and alcoholic OH both are present. So it is called enol form. So we have one type of tautomerism. We are going to discuss tautomerism separately, and this is only one example. We may have tautomerism in many different compounds, like it may be in the nitro compounds also, nitromethane, nitroethane, etc. So in other amides also, or it may be in other types of compounds. We will see the types of tautomerism. But here, ketone tautomerism is one type. That means they are rapidly moving structures. They are functional isomers. Is it not? The functional group is different. Aldehyde group, enolic group. They are moving from one to another. So they are interconvertible. Then they are called tautomers. Whereas earlier, functional isomers, they are not interconvertible. But here they are interconvertible. Both the forms exist together. Depending on the conditions we may have, depending on the solvent, temperature, etc., the percentage of each one in that mixture may be different. So these are called tautomers. Anyway, just make note of this. So we will discuss in detail about tautomerism later. So that is about the structural isomerism, which is also called as, what is the other name? Constitutional isomerism. Because in examination they have asked, say they have given two compounds, they have asked you what type of isomers are these. So they have not given like chain isomerism, position isomerism. They have given constitutional isomerism, which the name may be new for you. So that's why I have given. So they have not given position isomers or chain isomers or functional isomers. They have given constitutional isomers. Constitutional isomers, geometrical isomers, optical isomers, etc. So constitutional isomers. One of the types of constitutional isomers. So anyway, that is about structural isomerism. We come to the other one, that is stereoisomerism. Now stereoisomerism is also called as a space isomerism. Now stereo you might have heard of from different positions. Stereo. We are getting some sound or similar. So here also the atom contains different substituents or atoms or molecules or some other groups attached to that atom in different positions in space. So the spatial arrangement is different, that is all. So they are called, say, stereoisomers. Now such stereoisomerism is of two types. One is geometrical isomerism, another is optical isomerism. What is geometrical isomerism? Now, under geometrical isomerism, let us see the explanation. Have you studied about geometrical isomerism? Have you studied about cis-trans isomerism? Yes. So, if you take C4H8, this is called butane. Now, there may be two compounds, CH2, CH, CH2, CH. Another one, it is CH3, CH, double one CH, CH. One butene, two butene. What are these two? What type of isomers? Position isomer. Position of the double bond is different. Now here, if you take two butene, so we have already worked out some problem. So about a single bond, it is, say, cylindrically symmetrical. Is it correct? About a triple bond, it is cylindrically symmetrical. Is that right? About a double bond, it is not cylindrically symmetrical. So we have a double bond where there is a double bond in 2-butene. We take 2-butene. In 2-butene, say we have the following forms. So one is CH3, then H, CH3, H. This is one form. Another form is C, double bond C. It is CH3, H, CH3, H. So, what difference you find? In the first one, we find the similar groups are on the same side. H and H, CH and CH3. Similar groups, they are opposite sides. H and H opposite side, CH and CH opposite sides. Are they interconvertible? Answer is no. There is no free rotation about the double bond. Whereas about a single bond there is free rotation. About a triple bond there can be free rotation. But about a double bond there is no free rotation or restricted rotation. Due to this, say these two are different. Now the first compound in which the similar atoms or groups are on the same side, it is called cis form. The other one is called trans form. Cis means same side, trans means opposite side. So the first compound is called cis-2-butene. This is called trans-2-butene. So the boiling points, melting points, reactivity, everything is different. Now this is more stable, this is less stable. This has got higher dipole moment, this has got lower dipole moment. This is more polar, this is less polar. This is more soluble in water, this is less soluble in water. So like that, there is repulsion between methyl and methyl. Here there is no repulsion. Melting point of the second one is higher, melting point of this one is lower. Whereas boiling point of this one is more, boiling point of this one is lower. That means, what I mean to say is, these two are different compounds. They are not same. They are different from each other. Their properties are entirely different. Reactivity, property, melting point, boiling point, everything is different. So, these two are called geometrical isomers. Now, geometrical arrangement in space, they are different. So, this form is called cis form, this form is called trans form. It arises due to restricted rotation about a double bond. Now, if these two are same, CH3 and CH3, or H and H, what do you expect? Will you have that compound showing geometrical isomerism? For example, 1-butane. The answer is no. Because even if you interchange the groups, the compound is same. For example, 1-butane will not show this type of isomerism, namely geometrical isomerism. Why? Even if you interchange, it is H and H only. Or even if these two are interchanged, we have H with H or CH3 with H only. They are same compounds. So, for a compound to show geometrical isomerism, what is the condition? There should be a double bond due to which there is restricted rotation, and doubly bonded carbon atom should be attached to different atoms or groups. So, CH3 and H, CH3 and H. So, can this compound show geometrical isomerism? For example, we have A, B, C, D. What do you expect? It shows geometrical isomerism, is it not? So, if you interchange, then A is with D on one side, B is with C on the other side. Whereas here, A and C, B and D, the two compounds are different. That means these two must be different. It can be same as another carbon atom, or it can be different also. So, for a compound to show geometrical isomerism, there should be restricted rotation of double bond. Need not be between C and C, it can be between any two atoms, and then the doubly bonded carbon, for example, it should be attached to two different atoms or groups. So, we have identified this as cis form and trans form. I will give you another example. We have CH, then Cl, double bond, CH, that is C, Br, then I. So, can you predict whether it shows geometrical isomerism or not? What is the answer? It is chloro, 1 chloro, 2 bromo, or better, bromo first. That is 1 bromo, then 2 chloro, 1 iodo, ethene. Will it show geometrical isomerism or not? Answer is yes. No. Why? I can write C, double bond C. Then we have H and Cl. We have Br and I. If I take another one, we have C and C. Then it is linked to H and Cl. We have I and Br. These two are different. Cl and I on the same side. Here Cl and Br on the same side. Then which is cis and which is trans? Then there is some problem. So we cannot make use of the say prefix cis or trans. So we are using different say notation. It is called ZE notation. So what is Z and E for? Actually, the short form of Isomer and E from N to the Z. Not necessary. Isomer and N to the Z. So what are these? Isomer means same side. N to the Z means opposite side. Anti. Now, what is this? Now we give priority to the atoms joined to the doubly bonded carbon atom. What do you mean by priority? Higher the atomic mass, higher the priority. So between H and Cl, which is of higher priority? Cl. So between bromine and iodine, which is higher priority? Iodine. Then here it is Cl, it is iodine. When such higher priority atoms, they are on the same side of the double bond, it is called Z form. When they are on opposite sides of the double bond, it is called E form. Z form and E form. This is what I am just explaining to you. So between H and Cl, this is of higher priority. The priority depends on the atomic mass. So Cl is of higher priority than H. Similarly, between Br and I is of higher priority. So this higher priority, they are on the same side, Z form. They are on opposite side, they are E form. So this is Z form of that compound, E form of that compound. They write Z, then 1 bromo, 2 chloro, 1 iodo, a thene, like that. Similarly, E form. You can immediately write what is that compound. Hope it is clear. Now, there may be some difficulty in finding the priority. This is for halogens. Here, why are you in a hurry? Have you completed? So, therefore, here in this example, say we have taken hydrogen, chlorine, bromine, iodine. Now we will take another example. Now we have C, double bond C. Then we have CH3. Then it is C2H5. Then we have H. We have D. Now these two are different. Between H and D, which is of higher priority? D, because it is 1H2, higher atomic mass. Between CH3 and C2H5, so it is C2H5 because carbon is attached to one more carbon atom. So these two are on the same side, so it is Z form. When they are on opposite side, it is E form. We will take another example. We have H, we have Br, we have then it is Cl, we have CH2Br. We will take Br only. Now, in this case, so between H and Br, which is of higher priority? Br. Between Br and CH2Br, which is of higher priority? CH2Br. That is wrong. So don't be in a hurry. So what I said, it is wrong. So therefore, here it is Br of higher priority. Why? You have to take the first atom attached to this. The first atom attached to this is carbon. First atom attached to this is bromine. So if these two are not comparable, then you have to see the remaining. Because here it is C and C, both are same. Then you are taking the next one. Otherwise, not necessary. So C is attached to C here, whereas here C is attached to H. So C attached to C is of higher priority. Now here it is Br, it is C. So therefore this is of higher priority over. So this is of higher priority. Even though total mass may be higher, it is not the way of finding out the higher priority. Then if it is something different, you take different example. So what is this form? This is then opposite side. So it is E form, not Z form. Then take another example. CH3, C2, H5. It is C2, H5, C2, H4. So here it is the priority is between CH3 and C2H5, this is of higher priority. Between C2H5 and C2H4, this is of higher priority. C2H4 is of higher priority because C double bond C is considered as though it is C, 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 C attached to two more carbon atoms. As though it is attached to two more carbon atoms. Therefore, so here it is attached to only one carbon atom, it is attached to two more carbon atoms. Therefore, this is of higher priority. That is why. So it looks very simple in the beginning, like chain isomerism, position isomerism. As you move higher, geometrical isomerism, optical isomerism, it becomes more and more difficult. Problem will be asked. So you must be very careful to understand these types of things. So this is of higher priority because a double bond is considered as though it contains two more carbon atoms. Similarly, a triple bond is considered as though it contains four more carbon atoms. As though it contains four more carbon. So this form is called therefore Z form. Then take another example. C, double bond C. We have CH3, we have CH2, CH2, CH3. We have CH3, we have CH, CH3, CH3. or you can take a set group here, CH3, CH2, CH2. So between these two, which is of higher priority? It is 3 carbon. Oh. So between these two, which is of higher priority? Anyone? Right side. Why? Here, first is C. Same. Then C is attached to C. Whereas here C is attached to C. Is it not? Here C is attached to. So this is of higher priority. So this form is called Z form. That is why you must be intelligent. We are filtering the students. So here the carbon atom is attached to 2 carbon atoms and 1 hydrogen atom. Here the carbon is attached to 2 hydrogen and 1 carbon. This is of higher priority. 2 carbon instead of hydrogen. Here 2 hydrogen, 1 carbon. 2 hydrogen and 1 carbon. 2 carbon and 1 hydrogen. This is of higher priority. So therefore you must concentrate more. Word by word. You cannot miss. This means you are losing. Because every point that you are explaining in the class, they are all important. I have told you, more than 75% of the information is available in the class only. Not in that sheet. Just to follow, you are giving the, supplying the sheet. But how much you are absorbing, how much you are noting down, how much you are understanding, following, it is most important. So ordinary students may be difficult for you. So go on just trying to absorb as much as possible. Go on try to write as much as possible. And after going home, once again go through all these things. And once you have understood, then it will remain permanent in your mind. So you must understand well. Whereas right from first standard till now, many of you, almost all, they simply by heart study, write in the examination and forget. So if the same thing is asked after some time, you don't know anything. Most of you just think yourself, find out in yourself. So here it is not like that. Once you understood, means it will remain permanent. You will not forget. So therefore, be careful. Once again after going home, once again just go through this. So it will remain permanent in your mind. That is sufficient. Just find out yourself. I have given the different examples. So don't forget this one. Because later you are using the same priority under optical isomerism also. The same priority rules under optical isomerism also. So therefore, we have Z and E notation. So we have geometrical isomerism. We have two different structures possible. One is Z, if that is Z, the other one is the opposite. This E form, they are different. So they are not cis and trans. Even cis and trans forms, they can be called, this form can be called as Z form. It is a more common way of notating, that is showing in the form. So this is Z form. What is this form? This is E form. Instead of cis and trans, Z and E. You can make this form more commonly. Then, such type of geometrical isomerism may also take place in other different compounds. What are they? So, other examples for geometrical isomerism. Now, take this. pH, N, double bond N, pH. They are iso compounds. We have N, double bond N, pH. This is C. This is anti. Now the nitrogen atom here, it is sp2 hybridized. What do you mean by sp2 hybridized? Planar structure, 120. It is not linear. So due to this, double bond there is restricted rotation, and the two such groups, they may be same or different. On the same side means syn, opposite side means trans or anti. So these are also geometrical isomers. Geometrical isomers in azo compounds. Then we have oxides. Such oxides are compounds formed from aldehyde or ketones. So this is aldehyde, this is hydroxyl amine. Hydroxyl group, amino group. Then when there is reaction, you will get CH double bond NOH. This is oxide. Then aldoxides. So geometrical isomerism. So what are aldoxides? We have R, H, C, double bond N, OH. We have another one, R, H, C, double bond N, it is OH. The nitrogen atom is sp2 hybridized. H and OH, they are on the same side. It is syn form. They are opposite sides. It is antiform. Similarly, we may have ketoxides. So from aldehyde we have aldoxide. From ketones we have ketoxides. These are ketones are CO. Similarly, O and H2. So you will get oxide from ketone. This is called ketoxide. So what is the formula? We have ketone RCO. I will write in particular CH3 C2H5. CO means it is ethyl methyl ketone. Then ketoxide MOH. Then another form, it is CH3, then C2H5, then it is C double bond NOH. So these two are called syn and antiforms. So syn with respect to what? So ethyl, is it not? So it is called syn, then ethyl methyl ketoxide. It can also be called another name, anti methyl ethyl ketoxide. Anti syn ethyl methyl, anti methyl ethyl ketoxide. Similarly, this is syn methyl ethyl ketoxide, anti ethyl methyl ketoxide. They are also different. Why they are different? Which one? Syn methyl, these are on the same side, you know. Syn methyl ethyl, anti ethyl methyl, anti opposite. Similarly, syn means syn ethyl methyl, anti methyl ethyl. No difficulty now. Try to understand well. So therefore, are they not different compounds? They are different compounds. There is no free rotation about the double bond, restricted rotation. So their melting point properties, everything is different. They are also geometrical isomers. Then you take another compound, C, double bond C, double bond C, double bond C. We have A, B, A, B. Now, these are called allenes. What are allenes? Allenes are a class of compounds where the double bonds repeat one after the other carbon atoms. Now, say Here, this carbon atom is sp2 hybridized. What about this one? sp. This one? sp. This one? sp2. So, between these two, we have a pi bond. Is it not? Between these two, pi bond. How the pi bond? Here, we have A, B, C. They lie in the same plane. You know, this pi bond electron cloud above and below. Is it right? Then, this pi bond, is it in the same plane? Because it is sp. sp means 2 pi bonds. 2 pi bonds, are they in the same plane? There is one above, below, in front, behind. In triple bond, isolation structure. That means, say this electron cloud is in front and behind, not in the same plane. One is above, below, another in front and behind. And once again, here, it is in the same plane. Is it not? That means, if these are single atoms, like hydrogen, chlorine, bromine, iodine, hydrogen, chlorine, bromine, iodine, how many atoms are there in the same plane in this molecule? Totally. Hydrogen, chlorine, bromine, iodine. Totally, how many atoms? They are the same plane in that molecule. 1, 2, 3, 4, 5, 6, 7, 8. All of them lie in the same plane, no? But if it is CH3, then hydrogen atoms are in different planes because it is tetrahedral. If it is single atom, then it is in the same plane. Is it not? Now, will it show geometrical isomerism? Answer is yes. Because, say, other form will be, say, C, 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 C. So we have A, B, here, B, B. They are geometrical isomers. Now these are called allenes. In this, how many double bonds are present? How many double bonds are present? 3. In butane, which we have taken, how many double bonds are present? 1. So, if a compound contains 1 double bond, or 3 double bonds, or 5 double bonds, or 7 double bonds, or in allenes containing odd number of double bonds, it shows geometrical isomerism, provided these two are different. The terminal carbon atoms are attached to different atoms. If these are same, then no, just like one butane. So, allenes containing odd number of double bonds show geometrical isomerism, provided terminal carbon atoms are linked to different atoms or groups. If it is even, we are not considered now. We will come to that. Don't be in a hurry. We will come to that. The next, optical isomerism, not geometrical isomerism. Oh, if it contains odd number of double bonds, it shows geometrical isomerism, provided the terminal carbon atoms are linked to different different atoms or groups. So, it can be 1 double bond, it can be 3 double bonds, it can be 5 double bonds or 7 double bonds, provided it is allene. Allene means continuously, not it is cut in the middle in CH2. Continuously it is present, then only it is allene. So, that is another example for geometrical isomers. Remember, it need not be cis-trans. They are geometrical isomers. Then, take another one, cycloalkanes. Now, cyclopropane, for example, it is linked to X and X. Cyclopropane, it is linked to X and X. One is cis, another is trans. They are geometrical isomers. Similarly, you may have cyclobutane. It can be 1, 3 or it can be 1, 2 also. Similarly, cyclopentane. Yes, 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 yes. Need not be these two 1, 2. It can be 1, 3 positions also. And then also it is same. Yes, 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 yes. So one is cis form, another is trans form. Thus geometrical isomerism may be in these different forms. So one is cis form, another is trans form. Now one is Z form, another is E form, similar to what we have seen earlier. Then I think that is what we have just seen, discussed. Aldoxides, picoxides, alkenes, isocompounds, alkenes and cycloalkenes. We come to the problem. The sheet is already supplied to you. So the first problem. The total number of, just to try the first problem, the structural isomers. So include structural isomers, because later we should not confuse. Only structural. Total number of structural isomers having the molecular formula C4H10OR. C4H10OR. Can you just try yourself. How many structural isomers are possible? These are the type of problems that will be asked in examination. Two, 4, 6, 7. One correct answer out of this. So you want to get the answer as quickly as possible. So every time you have to solve the problem, don't guess anything. For solving the problem, you have to use quick methods. That means, for example, here if it is ethyl alcohol, we write CH2, CH3, CH2OH. Instead you can write CCOH. H, all of you know, primary means C, 3, secondary means 2, tertiary means 1 hydrogen atom. C, make the short form, CC, then OH, etc. For example, in this case, we have, there is 4 carbon atoms, so I can write C, 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 OH. There is one form. Similarly, another form, C, 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 OH. Like that, totally how many? How many different structural forms? Quickly you have to get the answer. You do not write CH3, CH2, etc. It may take more time. Totally. You must be very careful, because they are all problems asked in examinations. So don't be in a hurry to give the answers, because many they know that many of you will give some wrong answers. Answer 4 is wrong. Answer 6 is wrong. 7 is the correct answer. How do you get 7? That is important. It is not the answer that is important in all these problems. It is how do you get the 7 answers? What are these 7 different forms? That is more important. Yeah, write it. Write it yourself. Find out yourself. totally 7. These are the 7 different forms. I told you, you do not write H3, H2, etc. because it will be waste of time and you are losing some time. It is sufficient if you know these are different forms. It is 1 propanol. It is isobutyl alcohol or 2 methyl propanol. Then this is 2 butanol. This is tertiary butyl alcohol or 2 methyl 2 propanol. This is diethyl ether. This is methyl propyl ether. This is isopropyl methyl ether. All are different. Totally 7 different forms. Next one. Second. The various compounds having the molecular formula C4H10 are. Which one? C. Chain isomers. That is butane. C4H10 is butane. Normal butane and isobutane are the only two chain isomers. Third one. The isomer of diethyl ether is. Diethyl ether is. What is diethyl ether? This is diethyl ether. The isomer of this is. Which one? Option A. Tertiary butyl alcohol. Tertiary butyl alcohol. This one. Option A. Option A. If it is D, how many carbon atoms are there totally? 5. It is only 4 carbon atoms. How is it D? Only 4 carbon atoms are there. Diethyl ether. 1, 2, 3, 4. This is diethyl ether. This is diethyl ether. CH3, CH2, CH2, CH3. Ethyl and ethyl. Then fourth one. The compound which shows geometrical isomerism. Which one of the following shows geometrical isomerism? B. Option B. Next one. Number 5. The alkane. So you must concentrate more because otherwise you may not understand. Try to understand well. Not the answer. How is it? That is most important. Fifth one. An alkane forms monosubstituted isomers when the number of carbon atom is at least. An alkane forms monosubstituted isomers. Answer? Give the answer. 3. Answer 3 is the correct one. Because it is CH3, CH2, CH3. So, monosubstituted. When hydrogen atom is replaced by chlorine, you get CH3, CH2, CH2, Cl or CH3, CHCl, CH3. Is there any other product possible? No. So, it is propane. Is at least, remember, it can also be 4, but they are asking at least, minimum. It is 3. But ethane cannot, only 1. Methane cannot, only 1 product. No isomers. But here isomers. Then 6th one. The compound which is not isomeric with the diethyl ether is. Option D, last one. Butanol. D, butanol. 7th one. A compound has the formula C2HCl2Br. The number of isomers which are possible is. That means that there are 2 carbon atoms and how many monovalent atoms? 2 chlorine, 1 H, 1 Br, totally 4. That means as good as C2H4 means double bond must be present. So, how many isomers are possible? What is the answer?
From the CH2 HCl2Br.
Which problem? There is H, Cl, Cl, here. Then C, double bond C, H, Cl, Br, Cl, C, double bond C. This H, Br, Cl, Cl. Only 3. Answer 3. Next one, number 8. Among the following compounds, the one showing geometrical isomerism is because it is an isomer. Remember, they are asking the number of isomers. This is one isomer. And the same molecular formula, different formula. They are not asking about geometrical isomerism, only isomers. The next one, number 9. C. Tenth one. The number of structural isomers include structural. The 10th problem. The number of structural isomers possible by replacing one hydrogen atom of 2-methylbutane by chlorine R. Huh? 2-methylbutane. Here.